Hello everyone, thank you for the introduction. My name is Mojtaba and I am a PhD student in Leuven. In the beginning I wanted to say thank you to organizers Lisbeth and Sarah for the invitation. In this talk I want to talk a little bit about the construction of a mathematical model of biodegradation behavior of magnesium-based implants and numerical simulation of these mathematical models. In the beginning, just a quick talk about biodegradable metals. Talking about biodegradable metals usually is restricted to three main materials: magnesium, zinc, and iron. And of course, their alloys. The most shiny aspect of these materials is their great mechanical properties, and it's obvious because these are just metals. And just beside these great mechanical properties, there are also considerations, especially on the biocompatibility and contribution and metabolism of general aspects of the body. For example, for the magnesium, it has been proved that it has high level of biocompatibility and also contributing also conduction. It means that it contributes to the generation of the new bones inside the body. So it's not a very important problem with these three materials. It makes them really good candidates for some potential applications, especially in cardiovascular stents and orthopedic implants. Because my PhD project is mostly related to orthopedic implants, the example that I want to give you is more related in this regard. The disease on which we are working is osteoarthritis. You probably already knew that osteoarthritis is the degeneration of the cartilages that causes inflammation, pain, and loss of mobility in the joint. In hip osteoarthritis, it happens in the hip joint, in the cartilage that lies between acetabulum and the femoral head. The solution to this problem is a surgery called total hip replacement, in which the damaged joint is replaced by an implant that restores the functionality of the ball and the hip socket. First, the damaged head of the femur bone is removed, and then the surgeon carefully clears all the damaged cartilage and bone from the hip socket. In the next step, a metal socket as well as a liner is inserted into the cavity, and then the femur bone is hollowed up, and a long and narrow implant called stem is inserted, as well as a ball on the top. As you may see, the functionality of the joint is restored. But there are a couple of issues with these implants. One of the issues is, at the end of their lifetime, these implants should be restored and replaced. But during this removal surgery, part of the newly formed bone is also removed along with the implant, making it difficult to achieve further mechanical stability. One of the greatest solutions to this problem is making at least part of the implant from biodegradable material, which means this part of the implant is degenerated, is disappeared over time, and be replaced by the newly formed bone. This requires tuning the biodegradation rate of the implant to the regeneration rate of the bone. In this project, it has been done by creating a mathematical model to assess the biodegradation of these implants. The model workflow is just a cliche of just the same as other computational projects, that the underlying science is converted first to mathematical models, and these mathematical models are converted to computational models. The underlying science in this project at the first step is the chemistry of biodegradation. But in the near future, we have to add the physics of fluid flow in the perfusion bioreactors, as well as the biology of the new tissue growth, in order to capture more complex cell culture conditions and more realistic solutions. For mathematical models, we use a set of partial differential equations that are diffusion convection reaction equations to capture the mass transfer during biodegradation, and level set equation to capture the moving interface. And then these are converted to computational model by taking advantage of a combination of finite difference method, finite elements, scientific computing libraries, and open source solvers. At the first step, the chemistry of biodegradation consists simply of oxidation of the magnesium scaffold, I'm talking about magnesium, into magnesium ions and free electrons. These free electrons reduces water, releasing hydrogen gas and hydroxide ions. A combination of hydroxide ions and magnesium will form a protective film on the surface. slowing down the rate of degradation. But in the presence of some special ions in the medium, this protective film can be eliminated. Again, we have an increase in the speed, in the rate of degradation. So, in order to create a mathematical model out of this, the model should continuously and simultaneously capture first the dissolution of the metallic implant, formation of a protective film, and effects of ions on the elimination of this protective film. It's not that much difficult to create this. We just assume that we have two reactions. The first one, the formation of the film with reaction rate K1, and the dissolution or elimination of this film with the reaction of K2. By having some simplification and notation in order to not to repeat chemical components in mathematical equations, we can create a simple PDE for change in concentration of magnesium over time, a PDE for the evolution of the film over time, and a PDE for the changes of concentration chloride ion in the medium. There is something missing here, and that's the effect of the film that we want to have it to protect that's underneath implants. In order to do that, theoretically, we compute the maximum concentration that the film can have, and by considering its porosity and density. And then we penalize the magnesium everywhere that they have it in the equations, here and here. So this is the final form of the PDEs that we have in order to capture the mass transfer during this degradation of the implants. The next step, as I said, is identifying the moving interface, because we want to know how the implant is evolving over time. And it just can be used in so many applications such as design optimization or shape optimization. So we need a shape. There are different approaches to do that. Interface tracking methods that are similar to particle tracking, so you put some particles on the interface and track those particles. Interface fitting methods that you distort the mesh towards just based on the interface and solve the equations on the distorted mesh, and interface capturing methods. This is the method that we are using, and in this sort of methods, you usually define a criteria that defines that where is the interface, where is inside, and where is outside. In order to do this, we use implicit interfaces. This is just a very quick introduction to implicit interfaces for the ones who doesn't have background in mathematics. In implicit interfaces, we define a function that defines the interface inside and outside. Usually the root of the function is our interfaces. The only thing that we need to do is to track this function. For example, for one-dimensional implicit interface that can define a one-dimensional implant, x squared minus 2, the interface is the roots of this function. Everywhere that the function is positive is outside of the implant, and everywhere that is negative is inside. Now, if for any changes, if we would have any modification in the base function, for example, it would be x squared minus 1, it means that we have moved in the interface. In this case, for example, the implant is shrinking. The same principle can be applied to 2D or 3D functions. For example, for the circles, the interface is up inside and outside. The next question is how to define this fine function, where it comes from. That's where the level set comes into the game. The level set can define a PDE function, PDE equation for you, that by solving that PDE, you can capture the implicit interface. If phi would be a function of space and time, the level set equation would be something like this. Simplifying it according to the biodegradation phenomena that we have, we do not have any external velocity field, and we do not have any curvature now. In the future that we want to add tissue growth, we cannot eliminate these terms, but now it can be simplified to something like this. The last step is compute this V, and then we can have the final form of the PDE solved. In order to do this, we should consider that V is the shrinkage velocity of the scaffold. We can use Rankine-Hagenate equation to just get this V. But in order to know these terms, we should just zoom in the interface, and we see that we have a profile for the concentration of the magnesium or the metallic ions. Inside the scaffold, we have the C-sol, means that it's the concentration of that metallic ions inside the implant, and outside we have the saturation concentration, and then it goes towards 0. By knowing this and just inserting these terms into that equation and then reordering and getting it re-inserting into the PD, we will have something like this. And this would be the fourth PD to solve. By solving this, we can get the interface of the implant over time. Next step is constructing computational models. It's not feasible to just use commercial software packages that are very common among students in engineering sciences departments, because we do not have full control on how to solve these PDEs, and we also need high performance, and these sort of packages are not that much high performance. So we have to create our own software by taking advantage of numerical schemes. Here, for this example equation that was our first PDE, we use finite difference method for our temporal terms with an implicit backward Euler scheme, and finite element for spatial terms with a first order Lagrange polynomial as a basis function. What is also very important in our approach is the computational mesh. Our mesh is purely Eulerian, and it's not Lagrangian like there are some other studies in biodegradation or corrosion that they use Lagrangian mesh and then mesh elimination or continuous damage as the way to study the degradation. Here we have Eulerian mesh. We just mark part of the mesh as this is the scaffold, and technically speaking, these are where the phi function is negative. And then we need high accuracy at the interface, because everything is happening in this study, in this computation, is just happening in the interface. In order to do that, we need to refine the mesh adaptively. So the final mesh would be something like this. And in 3D, it would be constructed again like this, and these are just two different materials in one mesh. So the implementation of the computational model would be first mesh generation that has been done in this project using some high efficient open source mesh generators, and then implementation of the big formulation. But by considering the fact that a typical 3D simulation will consist of around 800,000 of elements and 500,000 of degrees of freedom, we need to go for some high performance techniques. I mean parallelization. In order to do that, we use message passing interface and MPICH in general as a open source implementation of this, and high performance domain decomposition to just distribute different nodes to different processors, and also high performance solvers. After implementing the computational model, the first step is verifying the code. It has been done by visual inspection of the results, of the post-process results, to see whether there is some weird behavior in the results or not. The first thing is the mass transfer and ion release. That for the screw that I showed you, it will be something like this, just a uniform mass transfer, uniform ion release, and no weird behavior. As well as the level set surface tracking. It would be like this. And as you now know, this is just a simple post-processing of that phi function that shows how the screw is degrading over time. Again, in the case of code verification, we're just doing so many and extensive convergence studies, both for mesh size and time step. And these are really crucial for in-house codes. This is, for example, the results of some primary mesh convergence studies, and it also gives us some clue about the timing that is required for different mesh sizes and mesh numbers. But a criterion that we are using for hydrogen gases, I will just talk in the upcoming slides. And also verification contains benchmarking of the parallelization. The first step, this parallel code should produce the same results as the serial code. And in the next step, we also just evaluate the scale up. I mean, by increasing the number of MPI cores or CPU cores, we should have a decrease in computational time. It can be just seen like this, that the time that required to simulate every 40 time steps, or runtime for each time step for one equation in a very big computational problems with, for example, 2 billion of elements. We can see the scale up. After the verification of the code, the next step is calibration of the model. There are different approaches to calibrate the model. I mean, from experimental perspective, and one is the mass loss. We can directly measure the mass loss, the mass that is lost from the implant over time, or we can measure a side product that is evolved. In this case, for magnesium, we can just measure the evolved or formed hydrogen gas. Why we need to calibrate the model? Because as you saw in the PD form, we have a couple of coefficients for diffusions and reaction rates that are unknown. I mean, these 4 parameters, 2 for the diffusion of magnesium and chloride ions, and those 2 reaction rates. These are used for the calibration. We use experimental setup like this. This is just a simple immersion test, no perfusion. The evolved gas is gathered over time, and this is just the same sample. And we can see the formation of the film over the surface. These red regions are the formed protective film on the surface. And it gives us some graphs like this that shows how it behaves over time. At the beginning, we have just one step, that is degradation is very fast, and then it slows down. The difference between these 2 graphs for computational data and experimental data is due to the uncalibrated model. So we need to calibrate the model. The calibration would be something like this. In order to do the calibration, we should consider that each simulation at its most simplified version requires at least 8 hours to run. So we need an efficient and high performance approach to run the optimization to decrease the number of iterations as many as possible. In order to do this, we use a Bayesian optimization algorithm that is very high efficient. It is in a category of stochastic optimization algorithm and not the gradient-based ones. But because it creates a probability tree out of the iterations, it reduces the number of iterations in a very good way. And the cost function to just perform the optimization is the root mean square error of the difference of computational data and the experimental data. And this is a sample output of that optimization for the Bayesian optimization, and it just moves towards the desired value. It converges through the desired values very fast indeed, and it chooses the points close to these desired values and not just stochastically. And this is just have a quick look at the other applications that we have just simulated using this calibrated model. For the degradation of a CT image of cross-section of the magnesium scaffold, the mesh would be like this, again, an Eulerian mesh. And this is the formation of the protective film, those red regions on the surface of the implant. And this is how it degrades, how the scaffold is degraded and how the protective film is formed on top of it. Both animations are at the same time, one with computational mesh and one without. This is also a zoom-out view of the same scaffold, showing the formation of the protective film over time. And in 3D, the same shape can be like this. A porous scaffold, not the same shape. The shape that you saw at the beginning of the presentation for the back of the implant. And the last step is model validation. This step is still taking place currently, and we use another experimental setup to do so. It is something like this. It's a very innovative approach that the evolved hydrogen gas pushes the water back into the reservoir, and we're just measuring the weight of the water. We can just measure the volume of the evolved hydrogen. And for validation of the model, we will extend the models into the way that it can capture the pH changes, and then we use this criterion in order to validate the models. As a conclusion, I showed you how we constructed a quantitative mathematical model to assess the biodegradation. And as I told you, in the new feature, we will add with the same principle, the tissue growth and the fluid flow perfusion models into it. And once fully validated, this can be used to find the right design and properties of biodegradable metallic implants. Thank you for your attention.